How did the birth of quantum mechanics take place? That's the topic today. The answer lies again in the ambiguity of light. Another important problem with light or electromagnetic waves was the blackbody radiation. A blackbody is a body that acts as a perfect absorber as well as a perfect radiator. It radiates electromagnetic waves over the whole range of spectral frequencies. It was genuine for scientists to ask, what is the distribution of photonic density over the wavelength? Physicists like Rayleigh and Jeans derived a classical equation for it. As per Maxwell-Boltzmann statistics, we know the probability of a particle to exist at a particular energy level is given by P of EI equals some constant times the exponential of minus EI by kBt. As per classical mechanics, the energy was continuous, as it was proportional to the square of the amplitude of the oscillating particles. Planck used this concept and said that the vibrating particles of a blackbody radiation behaves in a similar way, maximizing its entropy. The only change was that light is made up of discrete energy packets, and thus the energy would only be an integral multiple of h nu. Thus would be discrete. E of I is equals nh nu. Thus, photonic energy E was some constant multiplied by the frequency. E equals h nu, where h is the Planck's constant. Thus, energy of radiation will always be an integral multiple of these chunks. In this way, energy of light was quantized. So, the probability of a particle to emit radiation of energy Ei is given by the following equation. So, the average energy of frequency nu, E average equals summation over Ei divided by the summation over Pi. Substituting the values and simplifying the equation, we get the following. Now take a look at the numerator. We can infer that it's like differentiating the exponential term with minus d of 1 by kBt. So we get the following. Now we replace the numerator with the obtained result. We will now go back to the equation and see how this helps with simplifying the equation. So, E average equals whole divided by sigma Now we can take the derivative out of the summation and push the summation in. We get we know dx by x equals d of ln x from differential equation. Using this, on the equation we get d of sigma e to the power minus nh nu by kBt divided by sigma e to the power minus nh nu by kBt. And over here there is a d of minus 1 by kBt. Now this term we can write as d of ln summation over e to the power minus nh nu by kBt divided by d of minus 1 by kBt. We have got this up till now. Now we'll write this term as an expansion. So we get d of ln 1 plus e to the power minus h nu by kBt plus e to the power minus 2h nu by kBt dot 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 up till infinity divided by d of minus 1 by kBt. This is a GP series, and we know that the sum of an infinite CP series is given by the first term divided by 1 minus its ratio, which is e to the power minus h nu by kBt. Differentiating the previously obtained result, we get the following. Now, energy per unit volume in interval nu and nu plus d nu is given by the number of moles multiplied with the average energy. du equals average energy dN by V. Now dN is given by the following equation. From this we can derive the photonic density as follows. Thus we find an expression for the radiance. Now here we can say that there is an exponential decay for higher values of nu, and finally is consistent with the experimental result as shown in the graph. This was a revolutionary concept that marked the beginning of quantum mechanics and earned Planck his Nobel Prize.